equation. So the number of splits of energy of the orbit is equal to 2 multiplied by L plus 1, where L is the orbital quantum number of that atom, of that electron inside that atom. So, for example, let's suppose we don't have any external magnetic field B. So this y-axis represents the energy level. Now, the 1s orbit will have one energy level. The 2s will have its own distinct energy level. The 2p will also have its distinct energy level. Now, recall from our discussion on the quantum numbers, we said that the p orbital, or L equals 1, has 3 different orientations in space. So it has 3 different unique magnetic quantum numbers. Now, each one of those magnetic quantum numbers of the p orbital basically designates the orientation of the orbital in the 3-dimensional space. So we have one p orbit that basically lies along the x-axis, the second p orbital lies along the y-axis, and the third p orbital lies along the z-axis. Now, in the absence of any external magnetic field B, those 3 orbitals that each lie along the different axes will basically have the same exact energy level. However, if we take that orbit and we place it inside an external magnetic field B, as a result of the magnetic dipole moment, there will be a splitting of these 3 orbitals. That is, no longer will the energy level of those 3p orbitals will be exactly the same, but now they will have slightly different energy levels. And this splitting of the p orbitals as well as the higher orbitals, for example, the d and the f orbital within any atom in the presence of an external magnetic field, is known as the Zeeman effect. Now, how many splits will actually take place depend on this equation. So for the p orbital in which the L value, the orbital quantum number, is equal to 1, 2 multiplied by 1 plus 1 is equal to 3. Now, if we're dealing with the d orbital, for example, in which L is equal to 2, then 2 multiplied by 2 plus 1 is equal to 5. So if this was a d orbital, this would split into 5 different energy levels. And this is once again known as the Zeeman effect. The question is, why exactly does the Zeeman effect actually take place? Well, the Zeeman effect takes place because of 2 things. Firstly, we have the external magnetic field B, and secondly, each electron within any given orbital contains the magnetic dipole moment, which points along its own axis. Now, for the case of the p orbital, we know that each p orbital has its own magnetic dipole moment that points along its own unique axis. So basically, for the p orbital that points along the z-axis, our magnetic dipole moment also points along the z-axis. For the p orbital that points along the x-axis, the magnetic dipole moment also points along the x-axis. And we can argue the same exact argument for the p orbital that points along the y-axis. It will have the magnetic dipole moment that will point along the y-axis. Now, when each one of those p orbitals are placed into an external magnetic field, the external magnetic field will create a torque that must do work and rotate those magnetic dipole moments along the same direction as the direction of the magnetic field lines of that external magnetic field B. And the orbital that contains the magnetic dipole moment, which rotates the most, will basically increase in energy by the greatest amount, because remember, when torque acts on an object to rotate that object, it does work on that object object, increasing that object's energy. And so that means the thing that rotates most, the orbital that will rotate most, will basically increase in energy most. So once again, why does spectral splitting actually take place? Why does the Zeeman effect actually take place? Well, every electron contains its own magnetic dipole moment mu that points in some particular direction. When placed into the magnetic field B, the torque that acts on the magnetic dipole moment mu must do work to orient that electron's magnetic dipole moment mu along the same direction as the magnetic field lines. Now, any two electron clouds, any two orbitals that have its own magnetic dipole moment that lie along different orientations will require different amount of energy, different amount of work to rotate that magnetic dipole moment. And that will basically increase the energy of those particular orbitals by different amounts. And that's exactly why we have this splitting of the p orbitals. In order for us to be able to describe the quantum state of any atom using the total angular momentum quantum number given by lowercase j, we can use a method or a system known as the spectroscopic notation. Now, the spectroscopic notation basically utilizes three quantum numbers. So the principal quantum number, which is given by lowercase n, which is a positive integer that begins with 1 and increases by increments of 1. So n could be 1, 2, 3, 4, 5, and so on. Now, the second quantum number that the spectroscopic notation uses is the orbital quantum number given by lowercase l. But instead of actually using the numerical value, we use a letter. So when L is equal to 0, that corresponds to capital S. When L is equal to 1, that corresponds to capital P. When L is equal to 2, that corresponds to capital D. When L is equal to 3, that corresponds to F. When L is equal to 4, that corresponds to G, and so on. So basically, instead of using the numerical value for the orbital quantum number, we use the letter, but the letter is capitalized. Now, the third and final quantum number that we must use when utilizing the spectroscopic notation is the total angular momentum quantum number that is given by lowercase j. Now, in the previous lecture, we said that j can be calculated using the given orbital quantum number L as well as the spin quantum number ms. So basically, to use the spectroscopic notation, we have to actually know what the spin quantum number is. Now notice J can never be a negative value. J is always a positive value, where ms is either negative 1/2 or positive 1/2. Now, the spectroscopic notation for a single electron system, for an atom that contains a single electron, is given by this notation. So n, where n is the principal quantum number L, which is the orbital quantum number, and the subscript for L is J, which is the total angular momentum quantum number. So let's look at the following three examples in which we're going to use the spectroscopic notation to state the quantum state of our atom. So, example 1. Using the spectroscopic notation, determine the quantum state of the hydrogen atom in the ground state. So we're assuming we have a neutral H atom, and that means we have a single electron. So to use the spectroscopic notation, we basically have to determine what N is, what L is, as well as J. So, N is equal to 1, L is equal to 0, which basically corresponds to the uppercase S. So that means our N is 1, our L is S. What about our J? So remember, J has to be have to basically take the sum of the spin quantum number and